Well, it's a pleasure to be part of this wonderful opening conference. Thank you, Irfan, and thank you everybody who arranged for this to happen. So I will talk a little bit about the connections between quantum information and quantum gravity. This is currently a very rich and exciting field, and I'll focus very much on one aspect, and I'll try to tell you well, hopefully enough to take something away about that one aspect, but don't get the idea that this is anything like a real overview. First, let me start without quantum information. Why are we interested in quantum gravity? And I guess personally I'm interested for a number of reasons. One is very simple. The story of physics is a story of unification, of describing more and more different phenomena with fewer and fewer ingredients, and every time we have taken such a step, it's revolutionized our way of thinking about nature. And yet here we are with these two pillars of physics still standing separate: quantum mechanics and the classical description of space-time as a dynamical object, which has replaced Newton's theory of gravity. When general relativity came along about 100 years ago, we still haven't been able to put those two together, and I'm sure that we would learn really exciting things about how the universe started. We would understand whether time is fundamental, as it sometimes seems when you look at quantum mechanics and how it's formulated, or whether it's an emergent object, as pretty much everything else has been that we've come across when you look at it more deeply. We'll know what happens inside a black hole should you be unfortunate enough to fall into one, and what will happen to you when you reach the singularity there, or what really happened when the universe started. So those seem like important fundamental questions. I don't know how you can sleep at night without knowing the answer, and so we need to figure it out. The thing that we've sort of known for a few decades, but the degree of it has really dramatically increased recently, is the importance of quantum information and of really fairly sophisticated concepts in quantum information to that challenge, to overcoming that challenge of quantum gravity. I think it's now become very clear. Certainly, I've learned the hard way that I really needed to catch up on a lot of quantum information concepts, and it's been very, very rewarding. So what I will focus on today is not many of the other interesting stories: the black hole information paradox, the firewall paradox, and there's lots of other things we could talk about, entanglement entropy. I will talk about a particular quantity which has emerged as a surprisingly, ridiculously powerful tool called the generalized entropy, and hopefully I'll be able to explain what that is. This goes back, again, a few decades to a general relativity theorem that you can just prove within Einstein's theory. The theorem is called the area theorem, and it was proven by Hawking in 1971. And it was actually one of the first ways that you could constrain how much energy can be emitted in a merger of two black holes. Because it tells you that the final black hole that everything settles down to has to have more horizon area than the sum of the two areas of the black holes that went into the process. Of course, today we have much better ways of estimating what comes out, and we can even measure it. But the general statement that Hawking was able to prove is that the area of all the event horizons in the universe, of all the boundaries of the regions that we call black holes from which you can't escape, that cannot ever decrease in any physical process. In particular, if you have one black hole, if you throw something in, it's going to get bigger. Okay, that's perhaps intuitively not that surprising, but it's actually surprisingly hard to prove this, and he did. You have to assume something about the energy of matter. Again, that's intuitively clear. If you had like a chunk of negative mass and you dumped it into a black hole, and it was, let's say, a Schwarzschild black hole, well, you'd expect the mass of the black hole to go down as a result, and therefore the radius also to decrease. So it's clear that this can't be something that's totally decoupled from what matter is around. And so you have to assume that matter looks like it has positive energy density from the point of view of a light ray. That's a fairly weak condition, but still, In quantum field theory, you can prepare states, we now know, where this condition is violated. Not globally negative energy, but you can have regions where the energy density is locally negative. And so this condition is violated. And so in fact, the area theorem is not true, it's wrong. It doesn't actually hold. And ironically, it's precisely the famous Hawking evaporation process, which is an excellent example of a violation where the black hole shrinks due to the emission of radiation. So you might say, can we fix this? Well, yes, we can. I'm going to give you something that's not historically accurate. Bekenstein was not trying to fix Hawking's area theorem. He was trying to fix something else, which I'll get to. But what you can do is the following thing. You can take the area, and this is the area measured in certain units called Planck units. They're very small, 10 to the minus 33 centimeters squared. And you can add to it the von Neumann entropy of the quantum state restricted to the exterior of the black hole. Okay, let me call that S out. Again, those two things together, I don't have time to talk about this in this talk, but it turns out they're first of all better defined than any one of them separately. You actually know how to make sense of them, make them cutoff independent, and so on. But what's important here is that there's a classical area law which breaks down, but you can rescue it by talking instead about this generalized entropy, the area of the black hole plus the exterior entropy. And the reason that this is a sensible object to think about was in the end, of course, that Bekenstein proposed that black holes really have an entropy equal to this quantity. And so when we have a second law in nature, it can't hold just for the matter entropy alone, the same way that if I put a cup of hot tea in the fridge, that entropy will go down, but the fridge emits radiation and so on, heats up the room, and overall the entropy goes up. We can't just forget about the black hole piece. Okay, so this was the generalized second law. It's really just the second law once you include the entropy of black holes in the overall budget. And what Bekenstein was really trying to do was to rescue the ordinary second law from failure when you dump entropy into a black hole. Hawking radiation hadn't been discovered yet. He didn't know that Hawking's area theorem had a problem, but he was also rescuing Hawking's area theorem. These two things together, as far as we know, always increase in any physical process, just not separately. And in fact, we now have proofs in certain fairly general settings that this is true. Just to complete the old story, soon afterwards, of course, Hawking did discover through completely different arguments that black holes radiate, and it was very nice to see that in that process, even though the area goes down, the entropy of the Hawking radiation more than makes up for that, and again, the generalized second law is upheld. The thing that I want to take away from this is this key story that the generalized second law is simultaneously a statement about entropy and about geometry. It has the area of black hole horizons in it, and it talks about the exterior quantum state whose von Neumann entropy must be added to that. It has two limits you can take, one in which you set h bar to 0, and then the exterior entropy is not important. It's infinitely subdominant to the area term, and you get back Hawking's area theorem, as you should in a classical setting. Or you might consider a limit where there just aren't any black holes, in which case the statement trivially reduces to the ordinary second law. And so you see that it very nicely unifies two completely different seeming things. But again, in general setting, neither of the old laws survives on its own. Now, there is another spin I could put on what I just said, which is perverse because it's violently ahistorical. But let's just pretend for a moment that we were very good general relativists, but we had never heard of the second law of thermodynamics. And that we were somehow inspired to rescue a gravity theorem, this famous area theorem, from failure in a quantum process such as Hawking evaporation. We're trying to fix it up. And it occurs to us that maybe it helps to add the entropy of the Hawking radiation to it that's being emitted, or more generally, the entropy of everything that's outside the black hole. Hey, then it works, right? Now I could have taken a limit where there is no black hole, and my new law would still tell me that the entropy always increases and never decreases. And so I would have, as this incredibly ignorant person, I would have now discovered the second law of thermodynamics, starting from general relativity and sort of adding a quantum correction, then taking away gravity. I would have obtained this very fundamental law by this bizarre process. Okay. Now, of course, we already knew the second law of thermodynamics, so maybe that's not so interesting. But it raises the question, can we play this game again? Can we start with something else we know from general relativity and somehow put it on quantum steroids and then throw away general relativity and get something new about quantum mechanics or quantum field theory? And the answer, of course, is yes, otherwise I wouldn't be talking about it. And this is really something that was pioneered almost single-handedly by a guy called Aaron Wall a few years ago, this way of thinking about quantum gravity and about thinking about actually using quantum gravity to get new results about theories we think we already know. So in particular, one thing you had to do, and this is also due to his work, is you had to recognize that this notion of generalized entropy, which was central to my perverse argument for discovering the second law of thermodynamics, this notion of generalized entropy actually need not be tied just to the slices of a black hole horizon. So I was considering the area of a black hole horizon, the entropy outside of that, but in fact you can make sense of this notion, area plus exterior entropy, for any surface, as long as it sort of divides space into two pieces. It doesn't even matter which side you call the outside, it turns out. Just stick to the same side in the entire argument, everything will be fine. So we can now try to play a game. We can start with any compact two-dimensional surface, pick our favorite general relativity statement about areas of surfaces and things they do, and then see if we can get something useful out by simply adding a quantum correction to this area and then somehow trying to throw away the original GR part and keep the quantum part. And the thing I will focus on here, there are a number of different options, but the one that's been particularly striking because we're starting with something so trivial from the general relativity viewpoint. The area theorem, at least, was hard to prove. It's incredibly easy to prove that something called the classical expansion cannot increase in general relativity. The classical expansion is, think of some surface and you line it with laser guns or something on one side, and then you flash the lasers for just one instant. Okay, and then you ask, what do these laser beams do as they move away from the surface? And really focus on some small area element. Are they moving apart or together? Okay, so the logarithmic derivative of that cross-sectional area element is called the expansion. If it's positive, they're moving apart. If it's negative, they're moving together. So for example, for a sphere in flat space, if you send them to the outside, then they'll move apart, and to the inside, they'll move together. Negative expansion. Okay, so it turns out that the expansion, again, with reasonable assumptions about the matter content, this null energy condition, cannot increase. What that means is, for example, if you have parallel light rays, as you know, they're focused by the sun. The deflection of light by the sun will make them come together, so you go from 0 to negative expansion. They're not anti-focused. Okay, and this is a very simple version of what's called the focusing theorem of general relativity. Just the fact that the expansion will not increase, it'll decrease when light rays, fictional or real, I'm really just talking about null geodesics, encounter matter. Okay, so this is, we're just going to turn the crank here. The classical expansion is a derivative of an area. So we can also define a quantum expansion if we just add this quantum correction to the area. We basically consider the logarithmic derivative of the, more precisely, we consider the derivative of the generalized entropy per unit area. You have to be a little careful where you replace the area by the quantum corrected term and where you don't, and there's a bit of a dark art to it, of course. It's not that, but you get the basic idea. This is the thing that works. Okay, so we define a quantum expansion essentially the same way as the classical expansion, just with this correction that includes a quantum information quantity. And of course, the first thing I should say about this is that you can recover the classical focusing theorem as usual, and the h bar goes to 0 limit from this for the trivial reason that then this term is just not important and you're left with just the area. Okay, but now let's see if we can do something interesting. So our classical theorem was that the classical expansion cannot increase. You don't have anti-focusing. The quantum conjecture that we're going to make, obviously, is just exactly the same thing with the classical lowercase theta replaced by this quantum uppercase theta. And there's a bit more noise here because we have to use a functional derivatives for reasons that I can't go into, but it's really the same statement. Okay, so that's now a conjecture. We're just guessing this. We're guessing that this is true, and this is true even when the null energy condition which underlies this theorem is violated, for example, near an evaporating black hole. Okay, this is supposed to remain true. So we studied this for a while, and we realized that this quantum focusing conjecture is incredibly powerful, even though it comes from such a trivial classical statement. First of all, it implies as special cases a bunch of things we already knew, the classical focusing theorem, obviously, and I won't talk about it, but it implies that Bekenstein's proposal is correct. So if you believe our focusing conjecture, then certainly the generalized second law must hold. But I'll talk a little bit about a few other things it implies. The covariant entropy bound, which is again something that was already known as a conjecture, and I was actually fairly proud of it. Because it's a very surprising and powerful statement about how many degrees of freedom there really are in nature and that they scale like the area. And here you just get this as a, sort of garbage product of this particular statement as an aside. So it's really amazing how powerful this technique seems to be. But then we also got some new things. We got for the first time a lower bound on the local energy density in a quantum field theory. And we were able to, again, prove, if you accept this as a starting point, and formulate a new generalized second law that applies in cosmology. So you can make sense of the generalized second law, not just when there are black holes around, but in a universe like the one we live in that's expanding. So let me first discuss how this covariant entropy bound comes out. So the covariant entropy bound is the statement roughly that the amount of entropy that you can have in a region cannot be larger than the surface area surrounding that region. But that statement is actually false. It's, for example, false for sufficiently large spheres in our universe. If what you mean by inside the sphere is spatially inside, then it's wrong. What does turn out to be true is if you use as the definition of the inside, well, light rays that move away from those spheres and which are not expanding. And you follow those for as long as you like. The entropy of the matter that's found by those light rays is always less than the area you started with. Okay, and that's basically the statement. Okay. So you get that out of the quantum focusing conjecture by starting with a two-dimensional, this point here is a two-dimensional sphere, actually. Every point in this diagram is a two-dimensional sphere. Okay. And this is a bunch of light rays, of which, again, I'm just showing one, which is moving forward in time, but also sideways in space, because it's a light ray. And I follow those light rays for a while until I get to some other sphere. So this could be a bigger sphere, and then light rays are emitted by it, and then this second one here is just a smaller sphere. So r equals 0 is somewhere over here. Imagine rotating that around some axis. Okay, so it's like a truncated cone. And this is the exterior of each of these spheres. And I can ask what is the entropy in this region. I can add it to these areas. And since the generalized entropy, roughly speaking, according to this conjecture, has a negative second derivative, then as long as I start with a non-positive first derivative, in other words, I have light rays which are initially not expanding away from my initial surface, then the generalized entropy has to be smaller on the final surface than on the initial one, just by integration. Okay. And once I know that, so that's, then I can, again, break up the generalized entropy in these two pieces, ordinary matter entropy and area of each sphere, and move all the area pieces on one side of the inequality and all the entropy pieces on the other side. And we see now that especially the simplest case is the one where the second sphere is actually infinitely small. In other words, I followed the cone all the way to the tip. I followed my light rays all the way to the center of my original sphere. Then the matter that's crossing this so-called light sheet is just simply everything that was inside the bigger sphere, and its entropy is then constrained to be less than the area of the initial surface, which is the covariant entropy bound. So we get this sort of funny statement out that really in general space-times it's always true that the world is kind of like a hologram. You could store all of the information at a fixed density per unit area on the boundary. Now for something new. So we can break up the quantum expansion into a classical expansion and a derivative of the exterior entropy. And we can do that with one more derivative attached. And the key thing is not all these formulas here, but we know what drives changes in the classical expansion. It's matter energy density focusing light rays. Okay? So we can translate any derivative of the classical expansion into something that contains the stress tensor of matter. And then we still have derivatives of the exterior entropy appearing in the conjecture. This is the original conjecture, that the quantum focusing conjecture, the quantum expansion cannot increase. So now you can take a clever limit. Naively, this classical piece is dominant and this is a quantum correction because it has an h bar in it. But you can arrange things so that the classical piece is also order h bar by simply starting classically with zero expansion and then letting quantum matter doing the focusing. Okay, then both pieces will be order h bar. And moreover, the focusing, the strength of that is proportional to Newton's constant, so both pieces will contain g Newton in it as well. So you can divide out by that. And you end up with an inequality on the matter stress tensor, or more precisely, matter stress tensor twice contracted with the null direction, the light-like direction you're considering, but you can pick any. In terms of, well, so what's the lower bound on the energy density you can have at a point? We actually know that there cannot be a lower bound. On the local, there were average energy conditions if you integrate over large enough region or large enough light ray. But this is really on the local energy density. Well, how did we get around that? The lower bound is an information theoretic quantity, which is itself non-local. Okay? We know that if you want to make the energy density very negative, the price you pay is that the derivative of the rate at which you acquire information has to become quite negative as well, even more negative. Okay, so this is, I think, the best way intuitively to think about this right-hand side is that literally if you were sitting in some place and you had access to this yellow region and now you deform along some light-like direction so you have access to a little bit more. So in principle, you could be receiving some information. It's really the second derivative of the amount of information you already have, which forms a lower bound on the energy density that you can have at this point. So if you want to quickly ramp up, for example, the rate at which you're acquiring information, then you need to have, at that time when you're ramping up, a lot of energy density. If, on the other hand, you're comfortable with turning it off, you could even have negative energy density while you continue to receive information. Now, because G Newton dropped out, and this is a quantum field theory statement with only h bar in it, even though we got it through this bizarre convoluted way where we started with general relativity, we can actually try to prove it in quantum field theory, which is, after all, a theory that we understand pretty well. And we did, so far, for free theories, and for certain classes of interacting theories, it was proven by our postdoc, Stefan Leichenauer, and one of my students, Jason Culler. Now, of course, that's not a complete proof, and in any case, maybe quantum field theory is wrong, so we should also try to test it experimentally. I don't know how far we are from doing that, but I'm very encouraged by the fact that this center was founded, and we talk. All right, I have just a few more words to say about the last of these implications I mentioned, the generalized second law in cosmology. So when we say that the world is a hologram, I really mean that quite literally. So for example, here's our universe. This is us. This is a past light cone. Light travels at 45 degrees in these diagrams. And you can sort of visualize that our past light cone, if you follow it back, it gets bigger and bigger. But then actually the cross-sectional area of the spheres has to go to 0 again as you approach the Big Bang, because everything gets really small down there, because the universe is all contracted down there. And so there's a maximum area somewhere along the way. And that'll be true tomorrow as well. So that's our past light cone tomorrow, and that's the day after tomorrow, and so on. And I can connect all these maximal area spheres. And each of them has the property that the expansion of the light rays away from it in both directions is not positive, and so I can apply the covariant entropy bound to both sides of it. And so I know that on this entire green slice, our past light cone, the entropy is not bigger than some billions of light years squared in Planck units. Okay, that's about 10 to the 120. And since I can do this slice by slice, I really have something that you could call a holographic screen, in which you could visualize as containing all of the information at a density of no more than 1 qubit per Planck area. And we can prove stuff about this. So for example, we can prove that the area of this holographic screen cannot decrease. So it's a new area theorem. It doesn't apply to event horizons, but to this other object. And it's useful because it helps you also characterize in a quasi-local way where a black hole is. You don't have to know the infinite future. So we can prove this, but again, subject to this annoying null energy condition that also was underlying Hawking's area theorem proof. But of course, now we know what to do, right? We will replace area by generalized entropy, and then assuming, so we define a quantum holographic screen instead of the classical one. It's going to be pretty nearby. And if we accept this quantum focusing conjecture that I advocated in this talk, then it also follows as a consequence that the second law for cosmology, the statement that the generalized entropy increases along a quantum holographic screen, must be true. This is the summary, and I'll leave it at that, and I'll take some questions.
Sir Musko?
The event horizon is a classical notion. So in principle, you might think that the events which come from different points are quantum correlated. So so if you are trying to extend the notion of entropy, adding some quantum term, eventually you should make this compatible with extension of the notion of event horizon. So did you think on that?
So this is rigorous in a semi-classical limit in which you take the product of G Newton and H bar to 0. So in that limit, you can compute the position, for example, of an event horizon iteratively in powers of GH bar. And you do have control in that sense. Now, of course, in the real world, GH bar is not exactly, or not arbitrarily small. And so you could take different limits where you take very large black holes and very weak radiation to be physically close to this regime that we're discussing here. It's interesting that, so we are in a regime which is still fairly close to safety. We're not that far from just doing quantum mechanics or just doing general relativity. And yet we can learn new things about each theory by combining them into, plausible conjectures about quantum gravity just at that level. But of course, what we really want to do is take what we've learned from this and also go in the other direction and really in the fundamental direction of what is the theory, what is a theory that can explain why it was obvious from the start that there's only an area's worth of degrees of freedom in nature. What is and that's much harder, right? There's guesswork involved. And we can at best say that this is a hint that tells us a little bit about in which direction we should be guessing, what kind of theory we should be looking for.
Jeff? And then I have a question too. So. Jeff, do you want? Yeah.
So 20 years ago, Kip Thorne talked about time travel through wormholes. Mm-hmm. And one of the things he needed, but he didn't know the answer to, was negative energy density to hold them open. And how negative did he need? And so can you constrain time travel?
Yeah, this is
by
an
this
excellent,
lower
that's an
bound?
excellent question. This is, yeah, so this is one of the things that I didn't have time to talk about. It actually was also done by Aaron Wall. He basically took all those theorems that we have, no warp drive, no time travel, no avoiding of singularities when you fall into a black hole, so it's the singularity theorems. All of those things rely on the null energy condition. And so all of them, you might think, might actually be wrong. And there are entire industries of cosmological models that were built around the idea that maybe you could have a bounce, for example, instead of collapsing to singularity, and that may actually be our past. And it turns out that if you replace the null energy condition as your input assumption with a generalized second law, for which we have, I think, significantly better motivation as actually being true and really a fundamental statement, that you can prove or reprove all of those statements. And so that doesn't mean that you can't have a bounce, but it means that you pay conceptually an enormous price for it. You have to give up the generalized second law of thermodynamics for it. Similarly for time machines, warp drives, and other things. So sorry to be as... but I found this very satisfying because it really, I think, tells us how to really organize our thoughts and what are the fundamental principles from which things follow.
I have a naive question maybe, but can one think of your quantum null energy condition as a kind of cosmological zero-point energy?
Can one think of it as
on the right-hand side, that you have some kind of generalized zero-point energy?
This is for, yeah. No.
If it's finite.
The short answer is no.
Okay.
So first of all, I mean, there's a bunch of questions hiding in this, I think. One is, what do you do with the divergences of the entanglement entropy?
Yes.
The reason that those do not appear or don't spoil this formula or make it trivial or something is that what appears on this side is the second derivative of the entanglement entropy, and the divergences drop out when you take the derivatives. They're basically pieces which are constant at that level, and they just drop out, so you only see the change.
Right.
But then the statement itself is intended to hold for any quantum state, not just in the vacuum. So in the vacuum, it's actually fairly trivial. Both sides would just be zero.
Yeah.
What's interesting is that when you do have some non-trivial quantum state, the inequality continues to hold.
Okay. Thank you very much, Raphael, for a stimulating talk. And